Today we're going to talk about position, velocity, acceleration, all right? And we start with the position versus time graph to kind of think about this. If I put some function about a position, some position function, S sub t, all right? Here's what's happening. I started at the origin, so at time 0, you're at position 0. And you really have to think of this as a particle moving along. And say it moves up some distance. So if I'm a particle on a line, and I'm controlled, so it's like a car in a tunnel, all right? So here's the line. I'm going to call this 0, all right? And initially, whatever it is, it goes to some distance out. But then all of a sudden, it turns around and goes backwards for a bit. Then it turns around and goes forward again. So this is displacement. When I say position, it is displacement for us people who've had physics, not distance. All right. Now the distance this little thing has traveled is whatever this plus this plus this is. You know, the distance is, I went 2 steps forward, I went 1 step back, I went 2 steps forward. My distance is 2 plus 1 plus 2 is 5. My displacement in this case is only 3. All right. So again, distance and displacement are different. But if we look at this graph I have on the board, do we all agree that this would be a secant line? What's the rise? It would be some number of feet. What's the run? Some number of seconds. And if we do slope of that line, feet per second, position versus time, the derivative of the average rate of change will be feet per second. The instantaneous rate of change will be feet per second as we bring h to 0. So guess what? If I have a position function S sub t, and I take its derivative, the units tell us that this is the velocity. Now if you have a velocity, feet per second, and you take the derivative of that with respect to time, feet per second, all right, that is acceleration. And so the derivative of v is acceleration. All right. Now, believe it or not, you can take the acceleration and take the derivative of it. Now, we're not going to talk too much about it this year, but it's called jerk, and it's actually spelled J-E-R-K. So, have you guys ever been at the stop sign and hit the gas really, really hard, your head snaps back? Of course not, because it's illegal to squeal your tires. You've never done that. Point is, if you do that, when your head snaps back in your Mustang, that is from, all right, that is from the change in acceleration. That is a jerk. That's the rate of change in acceleration. At the stop sign, you have 0 acceleration. When you really gun your car and your head snaps back, that's a change in acceleration. That's the rate of change. As we go down, the derivative changes. And when we do this, we can, all right, make equations and problems, all right, that talk about position of functions. And the easiest thing I think I can do in this case is just go right to the book and work out an example problem, if I can get it into the window here. All right, and if I shrink up a little bit. All right, so here's a, we'll cut it off, but we can make up the words that we're missing. All right. Or else I could spend all day trying to get this in the right window. There, good enough. All right. So the position of a particle is given by an equation. Now, developing these equations is really hard in the real world. But we're going to, walk it forward. Run. Boom. This is the position f of t is equals t cubed minus 6t squared plus 9t, where t is measured in seconds and s is measured in meters. So find the velocity at time t. Well, we just talked about this. If I want to find the velocity of a position function, what do I have to do? All right, let's do it. A is, and I'm going to call it f prime of t initially. How about 3t squared, right? Minus plus 9. That is, you guys all agree, that would be the velocity function. And you know the first thing I do after I write this down? I saw that it factored. In fact, I see it factors again. And the great thing about these problems initially, and then the AP test, they often do this. Because then it says, what is the velocity after 2 seconds and after 4 seconds? Well, that's not that hard. We just simply have to plug it in. So I want v of 2, and I want v of 4. All right, I'll plug it in. And again, I'm not going to write this out. Everybody, I'm going to put it in this formula right here. All right? 2 squared is 4. 4 minus 8 is negative 4. Negative 4 plus 3 is negative 1. Negative 1 times 3, negative 3. And why would I mark this completely wrong? I have no units. Meters per second. No units, completely wrong. Listen, no units, completely wrong. The AP gives credit for a step, answer, and unit. 3 points. And if you can get 2/3 of the points, you get a 4. So you can't miss units. That's the easiest one of the 3.
You can't get a 4, you need to get a 5, right?
No, you can get a 4. You can get a 3.
I know.
Oh. So now I put 4 in. Do the same math. 16 minus 16 is 0. Plus 3 is 3. 3 times 3 is 9. Well, here's what I know. Guys, guess what direction I'm going at 2 seconds? Going backwards. And guess which direction I'm going at 4 seconds? Forwards. Oh, okay. So we know that. When is the particle at rest?
0 seconds.
What's at rest mean? The velocity is 0. So they want to know when v of t equals 0. So that's what it's asking. So I'm going to take my v of t up here, and I'm going to now factor it. Does everybody agree it's t minus 3, t minus 1? So what are the 2 times?
Could you put 0 and you put 1?
T equals 1 and 3. Now, we knew that because what theorem told us there had to be a velocity of 0 between here?
The intermediate value.
IVT. It said, hey, we know this is a polynomial. Does everybody agree? And we know it's continuous. We knew one endpoint was negative 3. We know the other endpoint was 9. Between negative 3 and 9 has to be 0. IVT. You just said it louder.
And that's how you win arguments.
All right, great. You're ready for Congress. Okay. Letter D. When is the particle moving forward? That is, when is the particle, when is it going in a positive direction? Guys, do we agree a positive direction is when v of t is greater than 0? So I want to know, and I'm going to take this function right here, when is this thing going in a positive direction? Well, I'll tell you what, the easiest way I can do this is I can make a table. So I have time, and I know 1 and 3 are my special times, all right? And I got t minus 3, I got t minus 1, and I have the resulting v of t. And I can ignore the 3, right, because it's positive. And we know this is 0, and we know this is 0. So at 2, this is negative, positive, this is negative. At 1, or less than 1, I get negative, negative, so it's a positive. And after 3 seconds, positive, positive, positive. So it's asking, when is it going forward? Well, again, this is interval notation. Not negative infinity. Less than 1, but what's the starting point of time? 0. Guys, we got to start at 0. So for this interval on this problem, all right, negative infinity time. Again, only Superman can make the Earth go backwards. Only Superman, all right, can do that. Black holes. Black holes. Who knows? If we can survive going through them, touche. Yeah, I don't know. All right. How about this though? Everybody, here are the intervals where the velocity is greater than 0. Poofta. All right, we keep on rolling. Go back up, read letter E. Draw a diagram to represent the motion of the particle. All right, yeah, now this is a little bit annoying. Does everybody agree? And again, if I put the position function here, it was t cubed minus 6t squared and plus 9t. What do you notice about the position function? I think it's factorable. All right, so I can write this s of t equals t times t squared minus 6t plus 9. Oh, looky, t times t minus 3 squared. Do we agree? So when is the position 0? when we look at this, the position is at 0 seconds, and so do we all agree S of t equals 0 at, so if I'm going to do a diagram, all right, here is my 0 position, okay, here's my position function, S, all right, I know I'm here at the beginning, and I know at t equals 3 seconds, I'm back here. Now initially, because the velocity is positive, which way do we have to go for a while? We got to go to the right. So if I'm going right, oh, thank you, I hit it wrong. All right, so listen, I go to the right for a while. Well, I also know that at 1 second my velocity is 0, and then I start going backwards. So if I plug 1 into the position function, 1 times 4, I get position 4. And then I turn around and I come back to here. Do we agree? I'm at 3 again. And at 3 my velocity was 0 again. Did everybody remember that up in the previous one? At 3 my velocity was 0. So what happens then? I turn around and I start going the opposite direction. All right? There is my position function E. Now, there's only one thing left. Think about it. We talked about distance or displacement. I bet you letter F is what's the distance for some time. Find the total distance traveled during the first 5 seconds. This is displacement. At 5 seconds, if you plug 5 into this function, it's going to give you this number right here. That is not the distance this particle traveled. All right, so everybody, for letter F, I want distance over 5 seconds. All right? So I will put S of 5 in first. And I will use the equation from letter E right here. All right? 5, and then 5 minus 3 is 2. 2 squared is 4. 4 times 5 is 20. I will tell you that S of 5 is 20 meters. So when I talk about distance, I'll do this in blue. I go 4 meters, I go back 4 meters, and then how far do I travel here? 20 meters. So what's my total distance? 28 meters. And we've just done a very fast example of this, which we'll practice again tomorrow. All right?